Welcome to the webinar Traffic Analytics for Next-Gen ZTNA, powering Zero Trust Strategies with Real-Time Network Intelligence. I'm Ariana Lin, Principal Analyst and Senior Editor at the Fastmode. And with me today, I have Tobias Roeder. Tobias has more than 8 years of experience in product development and currently works as an application engineer for the Deep Packet Inspection software RNS Space 2 at IPOC, a subsidiary of the Roden Schwartz company. We will begin with an introduction to ZTNA and the concept of continuous adaptive trust. We will then go into how continuous adaptive trust is powered by real-time identity and context awareness, which relies on advanced traffic visibility. This will be followed by a discussion on the types of visibility required by ZTNA, the degree of visibility, and the impact of a lack of visibility on network outcomes. Next up will be a session by Tobias, who will explore how next-gen deep packet inspection technology delivers the necessary visibility for ZTNA solutions. He will look at IPOC's cutting-edge DPI engines, RNS Space 2 and RNS vPace, and some of their key features, including encrypted traffic intelligence and first packet classification. Tobias will also demonstrate 2 use cases of DPI in ZTNA. If you have any questions during the session, please type them into the chat box on your right. We will get back to you during the session or after via your email. A recording of this webinar will be sent to your email once the session is over. So the findings presented in this webinar are based on a recent research report titled Next-Gen DPI for ZTNA, Advanced Traffic Detection for Real-Time Identity and Context Awareness. The report is jointly produced by IPOC, a Roden Schwartz company, and the Fastmode, and is based on a survey of 55 leading ZTNA vendors that took place from October to December last year. To view all findings from the report, please visit bit.ly/ZTNA DPI report or click on the link in the right column. Okay, so let's begin. ZTNA, Zero Trust Network Access, is a security model that is based on the principle of never trust, always verify. What this means is that trust is never implicitly assumed and needs to be explicitly granted for every single request. When we say request, we refer to a user's attempt to access a resource. Resources include applications, servers, files, or databases. This means the means through which a request is made, such as a smartphone, computer, IoT node, or API server, is referred to as the device. On this slide, we can see the differences between older perimeter-based security models and modern security models. A perimeter-based approach to enterprise security simply assumes that all requests from within the perimeter are safe and that traffic from outside needs to be monitored more strictly. In this model, trust is primarily granted based on the user's physical location. These physical parameters, however, have become increasingly difficult to define. Enterprise networks are gradually shifting to look more like the diagram to the right than they do the diagram to the left. With a large majority of users and resources now outside the on-premises perimeter, we see an inversion of the enterprise network. So this inversion is driven by several factors. Post-pandemic, the shift to remote working or work from anywhere has strewn employees across various different cities, states, countries, even networks. So not only does this mean that employees are no longer on premises or even near to the premises or in fact on a fixed premises at all, but it also means that they may no longer be accessing enterprise resources from company-managed devices. Since it would be quite difficult to remotely manage a device, the majority of requests will come from employees' own devices, referred to as unmanaged or BYOD devices. This adds a huge layer of complexity to legacy access control and security systems, as they can no longer rely on location-based or managed device-based policies. Authentication protocols need to adapt to verify user identities and assess their security posture of the devices in real time, regardless of the location or ownership, which is exactly what ZTNA offers. And of course, another huge factor is the migration to cloud and SaaS applications. Enterprises increasingly prefer to use cloud apps over on-premise apps due to their greater functionality, scalability, flexibility, and accessibility. With access from anywhere with an internet connection, the cloud further pushes the decentralization of work environments and opens up potential security vulnerabilities. ZTNA addresses these by using reverse proxies to prevent the discovery of cloud or SaaS apps and by implementing a decentralized approach where security controls are distributed and enforced at the application level. So other factors driving ZTNA's adoption include the rise in machine-initiated connections such as API requests or those from IoT endpoints, and the growing number and complexity of cyber threats. Okay, so central to ZTNA is the concept of continuous adaptive trust, which continuously evaluates the user's trustworthiness throughout the session as they perform actions, make new requests, and just navigate around. Based on the trust levels of the user at each and every moment, ZTNA decides whether to continue to grant the user access or to terminate access to the resource. By combining point authentication with continuous authentication, ZTNA minimizes the risk of unauthorized access or data breaches and enhances security by providing a more granular and adaptive control over access permissions compared to the traditional location-based controls. Okay, so before going further, let's quickly look at the current state of ZTNA solutions. Based on the findings from the research report by IPOC, we can see that the majority of ZTNA deployment models are hybrid, with very few deployments being entirely cloud-based or on-premises. This is in line with the trends we mentioned earlier, the move to cloud and SaaS applications and the growth in remote working. The next finding is that ZTNA solutions are rapidly evolving, with 9 out of 10 vendors having had major enhancements or complete revamp to their solution in the last 3 years. Additionally, over half of the vendors offering ZTNA solutions also offered other SSE components such as DLP, SWG, and CASP. Okay, so back to the concept of continuous adaptive trust. How does continuous adaptive trust establish the trustworthiness of the user at every moment? Well, it leverages real-time identity and context awareness. The identity and context of a request is determined by matching information in ZTNA databases with real-time transaction data. On this page, we can see the examples of information stored in ZTNA databases and examples of transaction data. Database information includes identity records such as user IDs, user categories, user roles, or device IDs. Transaction data includes information collected in real time, such as the number of active sessions, timing and frequency of access requests, performance metrics, and traffic anomalies. For instance, a user with the right role and credentials may request access to an application, but this request comes from a device that has not yet been associated with this user. Or the same user is found to be active on many other sessions concurrently. In both of these scenarios, real-time identity and context awareness enables ZTNA to decide that the user shouldn't be granted access and that other security measures should be taken. Okay, so here is an illustrated example. When the user makes the initial request, database information, including their ID, role, credentials, and privileges, is matched against live transaction data, such as the IP address, device posture, and the time of the request. Based on this, the ZTNA engine determines that the request is trustworthy and grants the user access. However, over time, the ZTNA engine finds that the user has accessed a specific service within the resource. Let's say the resource was a CRM application and the sub-service that the user accessed was customer records. With real-time identity and context awareness, the ZTNA engine notes that this category of user rarely accesses customer records, as they usually access, let's say, marketing automation integration services. Trust levels for this session then drop. A little while later, the ZTNA engine discovers that the user has attempted to download large amounts of data in a short time frame. It then decides to revoke access from the user and terminate the session and take further security measures, such as preventing anybody else from accessing the resource until the culprit is found. Okay, so establishing identity and context awareness comes with many challenges, such as an incomplete inventory of resources, devices, and users, definition issues, loose or conflicting policies, and a partial ZTNA deployment. One of the largest issues, however, is poor traffic visibility. According to the report by IPOC, 90.7% of vendors feel that poor traffic visibility is a challenge in establishing identity and context awareness, with 29.6% highly agreeing that it is a challenge. Okay, so what is traffic visibility? Traffic visibility, which can be referred to as analytics, observability, network monitoring, network intelligence, basically refers to gathering granular real-time insights about IP network traffic. In this webinar, we are going to focus on one method of traffic visibility, which is deep packet inspection, DPI. DPI analyzes IP packets using a variety of techniques, including pattern matching and statistical, behavioral, and heuristic analysis. It then classifies these packets and extracts valuable metadata, including performance metrics such as speed and jitter, and other communication details. DPI classifies traffic by protocol, application, and service type. For example, it can identify that a packet is using the HTTP protocol, is from the application Facebook, and is specifically from a Facebook chat message. Cutting-edge DPI engines such as IPOC's RNS-Pace2 and RNS-vPace leverage additional techniques, including encrypted traffic intelligence powered by machine learning and deep learning, and advanced caching. Tobias will explore this in more detail later. So what happens when there is a lack of visibility? Without traffic visibility, identity and context awareness in ZTNA is severely hampered because live transaction data is unavailable. Without live transaction data, ZTNA databases become stagnant, and maintaining and validating these databases becomes a very manual and error-prone process. This means that the information stored in these databases may not accurately reflect the current network environment, as they don't receive the latest updates on users, devices, and resources. Essentially, without the information provided by DPI, ZTNA cannot function as effectively, as it can't see what's going on in the network, who are making requests, where are these requests coming from, and what resources are being accessed, and so on. It renders ZTNA blind to the activities occurring within the network, as it cannot determine the identity of users, the context in which they're accessing resources, or the nature of the transactions taking place. This lack of insight undermines the core principles of Zero Trust, which rely on continuous verification and validation of user identity and context. This is exacerbated by encryption and the use of anonymization tools such as VPNs, which further conceal traffic information. Okay, so a lack of traffic visibility impairs ZTNA's ability to detect anomalies, identify unauthorized access attempts, or respond swiftly to emerging threats. It makes it challenging to differentiate between normal user behavior and potentially malicious activities, such as data exfiltration or lateral movement within the network. In the report by IPOC, over half of ZTNA vendors say that there will be a severe increase in security vulnerabilities if ZTNA is implemented without sufficient traffic visibility. Another 37% say that there will be moderate or mild increase in security vulnerabilities. Respondents also expect a severe increase in network abuse and a severe degradation in user experience, according to 35.2% and 27.8% respectively. As you can see on this slide, other negative outcomes include higher IT costs from tool sprawl, degradation application performance, and the non-optimal use of network resources. In fact, nearly half of ZTNA vendors feel that the lack of adequate visibility in ZTNA has led to a delay in ZTNA adoption, or in some cases, no adoption at all. The report also notes that traffic visibility is crucial for ZTNA automation, with 40.7% of respondents stating that it is highly important. Without real-time granular traffic insights, automating ZTNA processes will be quite difficult, as it lacks the necessary insights to train and improve automation algorithms. DPI-based traffic visibility not only powers ZTNA's continuous adaptive trust, but is also an important part of a comprehensive zero trust execution. A comprehensive zero trust execution includes the implementation of least privilege access and microsegmentation, enabled by DPI's fine-tuned application and service detection capabilities. DPI also supports the implementation of authentication methods such as single sign-on and multi-factor authentication with its behavioral analysis and threat awareness. DPI signature libraries are very frequently updated with the latest signature patterns, which enables universal coverage as well as a single data loss protection policy, as all application types used by the enterprise, including web, SaaS apps, and shadow IT, are covered. Advanced DPI engines such as IPOC's RNS-Space2 and RNS-VPace also enable support for encrypted traffic with the ability to detect and identify traffic encrypted with the latest protocols such as TLS 1.3, ECH, QIC. Additionally, advanced DPI powers next-gen ZTNA solutions, which are defined by their next-level performance, AI/ML-based automation, automatic network segmentation, as well as their support for digital experience monitoring, many-to-many and multi-tier access requests, and API originator identification. Tobias will explore DPI's performance benchmarks and its machine learning and deep learning capabilities in depth later. Okay, so let's zoom into what makes an ideal traffic visibility solution. In this section, we will focus primarily on the findings of IPOC's report. Earlier, we established the importance of traffic visibility for ZTNA, but what type of visibility do ZTNA solutions require the most? Vendors rated resource, device, and user identity as the most important visibility category, with 77.8% stating that it is a critical requirement for ZTNA. The remaining 22.2% feel that it is either important or good to have. This is followed by security information, which 66.7% of vendors say is a critical requirement, and access and usage patterns, which 51.9% say are critical. Other categories in order of importance are network, hosting, hardware and software data, performance metrics, and networking resource usage. What about the parameters that are required? Similar to what we observed on the previous slide, the identification of cyber threats are the most important, followed by information on irregular or suspicious traffic, with 68.5% and 57.4% of respondents stating that they are highly important respectively. Threat awareness is a key feature of DPI and, as we can see, an indispensable component for ZTNA. This is followed by visibility into applications, protocols, and then service types. Okay, so on this slide, we can see some of the traffic visibility issues impacting the effectiveness of ZTNA, with the largest issue being data being collected from various disparate systems and tools. Other issues include a focus on point rather than continuous data, or data not being granular or accurate enough. One small challenge is the ZTNA broker itself not being monitored for networking or security issues. Traffic visibility is unsurprisingly most important for data storage and collaboration apps, and least important for social media apps. 37% of ZTNA vendors say that traffic insights are highly important for data storage or collaboration apps, with the figure being 27.8% for business apps, 27.8% for communication apps, and only 13% for social media apps. Nevertheless, the bulk of respondents still feel that these insights are important. Lastly, we quickly look at the adoption of DPI for traffic visibility for ZTNA. DPI emerges as one of the most popular visibility solutions, with 53.7% of ZTNA vendors currently using DPI. Among these vendors, the bulk are using in-house DPI, followed by commercial DPI. Of the vendors not using DPI, 26.1% plan to do so in the next year, 21.7% plan to do so in the next 1 to 3 years, and another 21.7% plan to use it sometime in the future. Okay, so I'm now handing the session over to Tobias, who will explore DPI's technology in detail. Tobias will present the capabilities of IPOC's high-performance DPI engines RNS Pace 2 and RNS V-Pace, and how they empower ZTNA solutions with unrivaled application and threat awareness. Over to you, Tobias.
Thank you, Ariana, and welcome to today's webinar. As mentioned earlier, I'm Tobias Roeder, Application Engineer at Rohde & Schwarz. I'm excited to be here today and to be able to discuss the importance of DPI, Deep Packet Inspection, for ZTNA. IPOC, a Rohde & Schwarz company, is a leading provider of advanced future-proof IP analytics software that delivers real-time visibility of IP network traffic. Embedded into telco, networking, and cybersecurity solutions, next-gen DPI software by IPOC enables reliable application classification. Our company develops software solutions that empower our customers to understand their network data and help transform raw IP data into the network insights needed to analyze, optimize, and manage networks efficiently, and to ensure the highest connectivity and security. IPOC was founded as a software startup in Leipzig in 2005 and acquired by the Munich-based electronics group Rohde & Schwarz in 2011. Currently, IPOC has over 300 employees and a strong focus on R&D. So, let us now learn more about next-gen DPI. Our engines, named RNS V-Pace and Pace 2, are easy to integrate, simple to manage for OEM vendors of network analytics, network management, and cybersecurity. The technology has been used in many of the world's top 4G and 5G telco cores, networking equipment, and cybersecurity components. Famous companies using us are Microsoft, Exfo, Barracuda Networks, Cisco, Graphiant, and many more. So, what are the actual benefits of integrating next-gen DPI libraries into ZTNA use cases? First of all, you gain full IP traffic visibility up to layer 7 and beyond, including encrypted traffic intelligence. Overall, we support thousands of apps and protocols and metadata extractors. We support single-pass architectures, meaning all inspection stages, including our DPI engine, are actioned through a single-pass parallel processing architecture. This allows to pass the DPI metadata along to the other subsequent processing stages. Based on DPI, unauthorized and malicious users can be detected. And based on our application classification bandwidth, for certain service categories such as VPNs, enterprise apps, video and audio can be allocated and/or precisely routed. Overall, this allows for dynamic network scaling and WAN optimization. Based on our classification, including attributes, we are able to classify and decode, and also transferred content can be optimized. Summing up, our DPI engine enables discovery of sensitive data, real-time investigation of traffic abnormalities, and augments reporting with critical metadata. Next, let us jump right into the typical detection stack of one example flow. We define a flow or connection as a 5-tuple. In this case, it's a WhatsApp 5-tuple connection. Our engines detect according to the OSI model, meaning layer 3 and onwards up to layer 7. We also introduce an additional over-the-top application layer. We call it virtual layer 8. In this specific case, WhatsApp can be transferred over layer 7 protocols HTTP in legacy cases, TLS or HTTPS, RTP is done. On top of the application, we detect potential service types or attributes such as video, audio, chat, or file transfer. On top of the protocol and application classifiers, PACE2 and vPACE support additional metadata extractors. Typical examples can be information on bandwidth usage, traffic volume, encryption details, attachment types, as well as quality of service and quality of experience indicators, such as jitter, throughput, or packet loss. Both engines focus on encrypted traffic intelligence. We will discuss this in just a few seconds. Additionally, we support many other features and extensions via plugins. This way, we support first packet classification, which we will also discuss in a few slides, and support a custom service classifier for user-maintained signatures in JSON files. Additionally, tethering detection for hotspot scenarios or mobile user equipment. Summarizing other unique benefits of our commercial DPI engines are high performance in terms of throughput per physical CPU core. Depending on the traffic profiles, we reach 20 plus Gbps per core. Additionally, our memory footprint is highly optimized for small and embedded hardware, allowing for easy integration into CPE's customer premise equipment on MIPS or ARM version 8. Weekly updates combined with dynamic upgrade APIs allow for stable ABIs internally, and we are upgradable on a weekly basis for up to 3 years with no need for recompiling or relinking. The weekly signature updates include new applications and protocols, and also maintenance and updates on existing applications. As mentioned before, we support FPC, First Packet Classification, which is imperative for ZTNA use cases. The challenge here is for policy decision in making the initial verdict with the very first flow packet. In case of TCP connections, the first packet is an empty SYN packet. Therefore, our engine supports detection based on DNS cacher or trusted IP ranges. We also support service cacher or SICA, which is a self-learning algorithm using IP service and traditional DPI results to match the detected IP and port combination and map those for subsequent flows. You can also choose to use a combination of the 3 mentioned options. Now discussing the encrypted traffic challenge. Nowadays, over 95% of traffic is either encrypted by TLS or QUIC protocol. Even in case of upcoming fully encrypted handshakes, for example, ESNI, encrypted server name indications, or encrypted DNS messages, we are able to provide visibility using supervised machine learning approaches. Also, in combination with caching methods, we achieve highest classification coverage on nowadays encrypted flows. Summing up, both DPI engines, RNS PACE2 and BPACE, will augment ZTNA offerings. It's highly scalable, provides threat intelligence, and comes with a rich application signature set for ZTNA critical categories. Our small processing footprint and support for high-efficiency packet frameworks such as DPTK and BPP allow for highest throughputs. Additionally, first packet classification enables real-time and instant policy decisions. Let us now dive right into two typical use cases for DPI-enhanced ZTNA, starting with SSE, Security Service Edges. SSE comprises of a set of cloud-based access control and security services. An SSE solution can deploy RNS PACE2 or RNS VPACE as a DPI component over here. A shared source of cloud-delivered traffic intelligence leveraging DPI software form factor, lean implementation, and super fast performance. This would allow uniformity across SSE's entire toolset, specifically across access control and security rules, monitoring and reporting formats, and threat responses. It allows application signature updates to be accessible in real time and cross the entire network. Enterprises with hybrid applications and hybrid IT architectures in particular benefit significantly from having an SSE solution that is enriched with a shared DPI capability. The second option in green shows that SSE can also benefit from DPI that is deployed exclusively in ZTNA by tapping into security alerts. An unknown device or behavioral trigger such as work-from-home employee attempt to access non-authorized applications can preempt sister components such as the CASP, the Cloud Access Security Broker, the NAC, the Network Access Control, or the SWG, the Secure Web Gateway for web-related transactions. Another typical use case is IoT, Industrial Internet of Things. That domain is key in industry within smart manufacturing, where high-speed, low-latency applications control and manage a wide range of IoT assets and infrastructure. Smart manufacturing benefits from ZTNA as it enables IoT assets such as computers, robots, machines, wearable devices, sensors, vehicles, monitors, smart tags, meters, and cameras to securely access various applications hosted on-premise or in the cloud. This figure here illustrates a typical network architecture for smart manufacturing. In this use case, DPI equips ZTNA with fine-grained traffic analytics that support access control and security. So, what are the benefits? Using DPI in combination for ZTNA workflows, we are able to identify unauthorized IT devices and OT assets like remote terminal units or PLCs, programmable logical controllers. By using our Stage 4 IoT protocol decoders, you can also identify IT/OT asset failures or disruptions. for example a machine breakdown, alerts, or power issues. Additionally, we are able to identify device-related cyber threats like corrupted software, denial of sleep attacks, or device hijacking. On top of that, unauthorized resources like malicious sites or banned URLs can be classified using vPACE and PACE2. Additionally, we are able to classify and prevent resource-related cyber attacks such as ransomware, spyware, phishing attacks, data theft, and malware. Overall, using DPI can detect MQTT hijacking, Modbus hijacking, eavesdropping, or sinkhole attacks. All these points prove the importance of the gained visibility by DPI for ZTNA in an IoT environment. Thanks again for joining me. My name is Tobias Roeder. For more information, please check out our white papers, blog posts, and case studies on ipoc.com. Goodbye. I am now handing the session back over to Ariana. Bye-bye.
Thank you for the great presentation, Tobias, and thank you to everyone watching. To learn more, visit bit.ly/ZTNA DPI report. For more resources on this topic, IPOC has also recently published a white paper titled Real-Time Traffic Visibility for ZTNA with Next-Gen DPI. The link to the white paper is bit.ly/ZTNA DPI. It discusses and illustrates DPI's role in zero trust networks in detail and explores other use cases such as private 5G campus networks. And lastly, the FastMod has published a special edition ebook featuring Q&A responses from 43 leading ZTNA vendors, including HP, Aruba, Akamai, Sophos, and Okta. Their responses look at ZTNA more generally, including zero trust adoption trends, cloud-based secure access, and zero trust principles. To read the ebook, visit bit.ly/ZTNA ebook. The links to all these three resources will appear in the right column. And please email any questions you might have to ariana.lin@thefastmod.com, and we will get back to you as soon as possible. Have a good day and see you again.